In this video, I want to define an invariant measure in SU2, or in particular in the theory of groups, where we have integrals that are performed over a certain measure that sometimes is labeled like this, du, some other times it might be labeled like this, d mu, where mu stands for measure of u, and in this case, in this video, I'm going to use this symbol, and I will show you why, because we will use du in another way. So by du in this video, I will mean that I take the differential of the group, and I will show you that. So I will define a measure like this, and then we have a certain function f that depends on the group. Now we will think that the group is SU2, so the group in our case will depend on 2 squared minus 1, so 3 parameters. And the parameters that we will use, parameters, are the Euler angles in this video. And the method that I will describe is actually quite general, so you can use it for other types of parameters, not just Euler angles. Now, how do we define an invariant measure so that we can properly define an integration, some way of integrating a function that depends on the group? Well, in order to do that, you can remember, for example, from general relativity that when we have to integrate some function, we have an invariant element, volume element of the kind square root of minus the determinant of a certain metric, which is the metric tensor. So we take the determinant of that, the square root of minus g. The minus sign comes from the fact that the determinant g is negative. So in general, this square root of minus g could also be written as the square root of the absolute value of g, if you want, because we want to get something positive. And then we have d for x in general relativity. If we have 3 variables, instead of d for x, we have d3x, and so on. So this is the number of variables, or in this case, it will be the number of parameters. So we will have to do something similar to that. And we want to first define a certain tensor, and then we can define the invariant volume element like this. And how do we define the metric tensor in this case when we deal with SU2? Well, first we need to define the invariant line element, ds squared. This is something which should be reminiscent of special and general relativity, where ds squared is written in the form g alpha beta dx alpha dx beta. Now, in this case, how do we define this element? Where we have the matrix U, which represents the group. It is a 2x2 matrix which contains 3 parameters, and we have to find a way to write an invariant element, line element. Now let me write an invariant element, and then I will explain why the expression is invariant. ds squared can be defined as 1/2, so this is just a factor which is not so important. But now comes the important part. We take the trace of du, and by du in this case I mean the differential of u. So I have a 2x2 matrix A, B, C, D, for example. I can write it like this. You have to remember that A, B, C, and D in SU2 should satisfy some constraints. U dagger U should be equal to the identity, right? Or if you want U dagger equal to the identity. If we take the differential of this matrix, we define the differential like this. So we take the differential of the first element, dA, then the differential of the second element, then we have dC and dd. So in this case, it's the differential of d, which, I mean, this is not really nice notation, but you should understand it. Now, in our case, these parameters actually depend on 3 angles, because we are using the parameterization of Euler. So it's the Euler angles parameterization. And so here, this is how you should interpret the differential of u. We will do the calculations with MATLAB, so don't worry too much. I will show you a script that will simplify all the computations that will have to be made. Then here we have du dagger, where this dagger, of course, means that we take the complex conjugate, and then we also take the transpose of the matrix. Now, why is this quantity invariant? So it's a scalar because we are taking the trace. du dagger is a matrix because we are multiplying two matrices, two by two matrices, and then we take the trace of that. This is invariant if, for example, we define or we transform u according to the following transformations. So we can do u goes to uv, where v is another unitary matrix, so it satisfies v dagger v equal to the identity. But we could also define u like this, so we transform u like this. We take v on the left and we apply it to u, or we can also transform u like this. It goes to u inverse. Now in this case, u inverse is equal to u dagger. Now you can easily show that this quantity here, this trace, will remain the same, so it is invariant if u undergoes the following transformations. For example, we can take the first one. So we have the trace of du becomes du v, and then we have v dagger du dagger. And here you can see that v dagger will give you the identity. And let me tell you that you have to think that v is independent of the three parameters. So when we take the differential of this quantity, we only have to take the differential of u because v is constant. Similarly, you can show that if you make this transformation, this trace will remain invariant by using the cyclic property of the trace. And quite easily, you can also show that if you make this transformation, the trace will remain invariant, which is not so difficult to show. It's actually very simple if you know the properties of the trace and the properties of unitary matrices. So this is a well-defined invariant element, and by invariant we mean that it is invariant under this kind of transformation, so under unitary transformations in particular. These are the important transformations also in the theory of loop quantum gravity. We want our theory to be invariant under unitary transformations of the SU2 group. Now when we take the trace here, and I will do that with MATLAB because I don't want to do these computations here, we will get something like this. We will get some quantity that multiplies d alpha squared, where alpha is one of the Euler angles. Then we get a plus, some other quantity that multiplies d beta squared, the other Euler angle, plus another quantity that multiplies d gamma squared, the other Euler angle, and then you can get cross terms. You get something that multiplies d alpha, d beta, and so on. You also have cross terms in alpha and gamma and beta and gamma. So I will not write these terms. But once you write down the invariant line element like this, well, it's quite easy to obtain these elements of the matrix G alpha beta, right? Because dx alpha or dx beta here will be of the kind, so dx alpha will be a vector given by d alpha, d beta, and d gamma. All right. So you can expand this expression, and you can equate term by term what you obtain from here with what you obtain from here. So you can define g alpha beta in terms of Euler angles. And now let me show you the script that I have prepared. In particular, this MATLAB script creates some symbolic variables. In particular, this one here, sigma 1, is the Pauli matrix sigma x or sigma 1. Then I define sigma 2, which is the Pauli matrix sigma y or sigma 2. And sigma 3 is the other Pauli matrix. Then we define this du, which is the differential of the unitary matrix u, which is defined in terms of the Euler angles. Let me remind you the expression for u defined in terms of Euler angles. In particular, this is a product of three rotations, and each rotation can be expressed by means of a complex exponential. So we have, in particular, e to the minus I alpha over 2 sigma 3 e to the minus I beta over 2 sigma 2 e to the minus I gamma over 2 sigma 3. Now there are formulas to write down the exponential of a matrix that depends on a Pauli matrix. And I mean, that formula is unnecessary because MATLAB can do it by itself. I have defined the expression here. So I have the exponential of a matrix in MATLAB can be obtained by using this function expm, expm. I have minus I, 1I is the imaginary unit. Then we have alpha, which is the variable alpha, the angle alpha. And then I multiply by sigma 3 and divide by 2. Here I have the exponential e to the minus I beta sigma 2 over 2, and then I have the exponential of minus I gamma sigma 3 over 2. And here, as you can see, I define the three Pauli matrices term by term. So we have the 1, 1 element, the 1, 2 element, the 2, 1 element, and the 2, 2 element. And you define them. And here you can see that I also define ds squared. This is ds squared. ds2 is ds squared. I define the matrix G and also its determinant G that we will calculate here in the script. I also define the angles, the Euler angles, alpha, beta, gamma. I define them in such a way that they are real, because I know that they are real parameters, whereas sigma 1, sigma 2, sigma 3, they are matrices and they can contain complex numbers. du is in general a 2 by 2 matrix, which can also be complex. It can contain complex numbers, whereas ds2g and that g, this determinant, they are real quantities, but I will not do computations with them. I will only define them. So I can define them like this, very generally, without specifying that they are real, but you can also define them as real quantities because they are real. In this case, I define the Euler angles to be real because when MATLAB does its computations, it has to know whether these are real quantities or complex quantities. And I mean, it will simplify the calculations in general. And then I define the differential of alpha, the differential of beta, and the differential of gamma. And I calculate the differential of u like this. I take the derivative of u with respect to alpha, and then I multiply it with d alpha. And then this is just the chain rule. So I have plus the differential, sorry, this is the derivative. When you see diff, this is the derivative of u with respect to beta. And then I multiply it by d beta plus the derivative of u with respect to gamma multiplied by d gamma. Here I define ds squared to be 1/2 the trace of the differential of u multiplied by the complex conjugate transpose, C transpose. This is a function in MATLAB that does that, of du. So this is du dagger. This quantity here that I'm highlighting is du dagger. And here I use the function simplify to do the calculations and simplify the expression. You can see that I have already run the script here on the right. So ds squared is this quantity here that you can see, where this d lowercase alpha here, this d subscript alpha is d alpha, is the differential of alpha, ds squared. And in MATLAB, here you see d subscript alpha, but it's d alpha squared. So I can also write the expression here. Let me create two different screens. I have ds squared equal to d alpha squared over 4 plus the cosine of beta d alpha d gamma divided by 2. Then I have plus d beta squared over 4 plus d gamma squared over 4. So this is quite a simple expression. And MATLAB calculated it starting from u. So you can, let me show you the expression for u. For example, I have to rerun the script. Let me see. And you see the expression of u here. If you want, we can also simplify that a little bit, like this. Let me rerun the script. So you can see that this is the expression for u. And this is how MATLAB outputs the expression. It's something that we saw in a previous video, but never mind. ds squared, and then it also calculates g. And how does MATLAB calculate g? I have defined g here in these lines. So in particular, for example, the element g11 is defined to be the second derivative. So it's a second derivative because we differentiate with respect to the alpha and then again with respect to the alpha. And I differentiate the element ds squared, and I also multiply it by 1/2. These are just some factors that are not too important, because what really matters is the invariant part, and if we multiply the invariant part by whatever constant we want, we still get an invariant quantity. We can multiply the invariant part by whatever number we want. But in general, so this is how you can calculate the elements. So let me write down the expression for g11 here for better readability. We have the second derivative of ds squared with respect to d alpha squared multiplied by 1/2. So this seems quite a complicated expression, but it is convenient to write it like this because MATLAB can compute it. And let me give you some intuition behind it. Well, ds squared can be written like this, right? So if we take the derivative of this quantity with respect to d alpha, we get so this will become 2d alpha over 4, and then we also get a derivative from here, which is plus cosine beta over 2 d gamma. Now we take the derivative with respect to the alpha again, because we have to take a second derivative, so this will give 0, whereas the derivative of the alpha will give us 1. So the derivative will give us 1/2. If we multiply it by 1/2, we get 1 over 4. So this will have to be equal to 1 over 4. And it's easy to see that this is the correct answer, because ds squared can also be computed from here. And so in this case, we are interested in the 1,1 element. So when we expand this expression, summing over alpha and over beta, the 1,1 element will multiply dx1 squared. But dx1 from here, you can see that is equal to the alpha. So we have the alpha squared here. So g11 should equal what multiplies the alpha squared here. So you can see that the alpha squared is multiplied by 1 over 4. So g11 should be equal to 1 over 4. And here we get the correct expression, right? And then you can understand why in MATLAB I defined these matrix elements in this manner. So for example, g12 is equal to the second derivative of ds squared with respect to the alpha and the beta multiplied by 1/2. Then G is a symmetric matrix, so G21 is equal to G12, and so on and so forth. When we compute the overall matrix G, this is what we get. Then here we can compute the determinant, or to be more precise, the square root of the determinant. So here I made a small mistake in the sense that this det G is not really the determinant of the metric, but it is the square root of the determinant of the metric, because I can see it from here. I define it to be the square root of the determinant of G, and then I simplify the expression. So it would be more convenient to write it as a square root of determinant of G, and I have to define this quantity, that G, to be SR sub that G. But this is just a definition after all. I can call it whatever I want. But the square root of the determinant of G is equal to, as you can see from here, square root of 1 minus the cosine squared of beta over 8. But 1 minus cosine squared is equal to the sine squared. So we get the square root of sine squared of beta divided by 8. So this is equal to the absolute value of sine beta over 8. And this means that we can define our invariant measure d mu u. This is equal to the square root of, in general, we have the absolute value of g, and then we have d3x. In our case, d3x is equal to d alpha, d beta, and d gamma. So we get the absolute value of sine beta over 8, d alpha, d beta, and d gamma. Now, if beta is an angle that goes from 0 to pi, sine beta is positive, and therefore you can remove the absolute value. And that's it. That's how you define the invariant volume element in SU2.